A rubber band is a great example to use to look at a non-linear force, all right, or a non-constant force. So a rubber band is going to act like a spring, but it's not always the case. It's going to be a non-linear material. So think about a rubber band for a little bit. You can stretch it, and then all of a sudden it's going to kick into what we call an elastic region, which is going to have it act like a spring, but it's not going to behave the same way. So we have a problem here where the rubber band tends to be a nonlinear material as compared to the spring, and we can actually represent the restoring force by a particular equation. So I'm going to give us the equation of negative 20x minus 3.7x squared. And the coefficients are in Newton meters for the x, and the 3.7 has Newton meters squared. But what we want to do is we want to calculate the change in elastic potential energy when the rubber band is stretched from 0 to 0.26 meters. So we're going to get that stretch. It's going to behave like a spring, and it's going to want to restore its original shape, and it's going to come back together. So if we think about energy and work, we know that the change in potential energy is equal to the negative of the work times the distance. And when we've done that before, I've got a graph here of a situation. We can look at it as terms of that integral. Now, I know most of you haven't gotten to integration yet, so we're going to kind of walk through this. But we also know that the integral deals with the area under the curve. So I'm going to use that equation that we had, the negative 20x minus 3.7x squared, and those two coefficients, and I am going to actually plot it. So I used Excel to do this plot. I've got my position, and I've got the force that's calculated. And we know that the work being done is going to be the opposite of our change in potential energy. Much like that in the slide problem, carrying the kid from the floor or from the horizontal ground to the top of the slide, the work that was done was converted into potential energy. So it's that change in work and change in energy, work energy theorem. So if we did this using the area, I can figure out each block on my area is going to be 1 Newton times 0.05 meters, or 0.05 Newton meters, or 0.05 joules. Now, when we have an incomplete block, I'm going to have to do an approximation of that area. And essentially, this is exactly what an integral is doing. It's summing up. Now, I can get better and better by narrowing each one of these different blocks, but for right now, I can actually just do it from the position. Now, I'm going to do it from 0 to 0.26 meters, so I'm only calculating this area here. Now, if I wanted to, I could flip this graph over. It would look a little different, but the area is still going to be the same. So I've calculated the area, and I've counted up all my blocks, and I'm getting that this is about 0.70 joules. And again, this is an estimate because I don't have a very finely incremented set of blocks. The more blocks, the more incremented I get, the better my assumption becomes, which is where that differential in x comes to be, that we want to make this small. So let's look at it in terms of when I actually do the integrating. And as we've seen before, anytime I have an integral that's got a x to some nth power and I integrate, it's going to equal a x to the nth plus 1 divided by n plus 1. So if I did this with my 20x dx, I'd get 20 divided by 2, and I'd get my x squared, and I would end up with 10x squared. And we can use this rule that says if I have two equations that are added together, I can do the individual integrals, and so that I can actually calculate using my integral here. In this case, we're using the minus 20 and the minus 3.7, and we get our equation. Now we're going to evaluate it from 0 to 0.26 meters. And when I do that, I'm going to do my final minus my initial, which is exactly what I've done here, and we end up with a negative 0.698 Newton meters, or negative 0.698 joules. So if the change in elastic potential is opposite that of the work, then I end up with 0.698 joules. Now, I want you to look at this number. If I round that to two significant figures, I get the 0.7 that I got there under the curve. So like I said, this is a really good example to look at that work area under the curve and to be able to do the problem that we've had by either using a graphical technique, which is essentially what my integration is doing for us, or by the integral technique. Hopefully this helps, and we will talk to you soon.